Hi everyone, thanks for joining our session. This is Srinivas Brahmaroutu and Morgan Bauer. Wei Hong, he could not make it to this conference. He's the one who brought us this use case. He's been working on this for about a year through lots of changes that happened. And finally we landed with custom resources at this point. We'll talk about that and have Morgan kick off.
Testing. Okay, good. Yeah, like you said, this is a use case brought to us by a coworker who works locally with us at IBM in SVL, which is in San Jose. And fault-tolerant custom resource controllers. So let's begin. We're going to go over what are CRDs, why they have how they're basically like standard API objects, and why you need a controller to perform actions. An important part of the fault-tolerant bit is the leader election process. Why you want your stuff to be fault-tolerant in general. We have these different use cases, these different patterns that that Wei has noticed that exist when the controllers have been implemented internally. And so we're going to go over the two that we have here that are called controller and controllee. I'm sure this is a pattern that already exists and has some official name, but we wrote the slides when we wrote the slides. And then we have some basically best practices on namespacing and implementation details, etc. So let's begin. What do we have? We have custom resources and controllers. So we have this new, well, it's relatively new in the last year or so. CRDs, custom resource definitions, have become a thing. It allows you to extend the API server with objects that only existed at runtime versus needing to be compiled into the API server and connect to the etcd backend. I work on one in Service Catalog, which is an actual API server versus the custom resources, so I'm familiar with the difference. The other side of course, of the API server is the controller model, and so you have to have a controller that either sees the CRDs or creates the CRDs, and this implements the standard sort of spec and status declarative model that Kubernetes has. Other implementations of this you've seen, obviously during the conference. The big one is the operator pattern, and then at least I've seen during the conference that the controller sort of SDK, cube builder, stuff like that now exists, and you should probably be using one of those. So how did this come about? This came about because Wei has been implementing an actual CRD controller and CRD use case in the back end. Started out with extending the actual Kubernetes code base with a bunch of private patch sets that were maintained on top of the Kubernetes source code and then carried forward from the 1.4, 1.3, 1.5 time frame. And then this is obviously not good when you can't really feed this back into the community, the APIs that you require, and thus now you have to rebase on changes that really you didn't know were going to come. I mean, you knew stuff was going to change, but you had no input on it. And so carrying those kind of patches forward is very time consuming and frustrating. So they took it from, once TPRs became a thing, they took these custom definitions from in-tree source to out-of-tree source and definitions. TPR sort of never got off the ground in a great way. It was marked as beta, but was never beta in the way that beta is typically used inside of the Kubernetes code base. It had lots of things that were broken from the beginning that some of them got fixed. And basically CRDs is third-party resources version 2. And around the 1.7, when CRDs became a more official and likely to be supported thing, they switched from TPRs to CRDs. Okay, next part is the leader election. So you want your controller to be able to be fault tolerant, and one of the ways to do that in terms of, a node goes down or your leader crashes or whatever, is to have a quicker ability to know that it's dead and either fail over or restart it. Leader election is one of the modes provided by Client Go toolkit, and so that they've taken advantage of this sort of provided functionality. So if we think through some of these use cases on, well, why can't I just say, give me 5 copies of the controller, and if one goes down, the other 4 can keep going? Well, at least in this object world, you don't want to have 5 different controllers getting the same resource watch update stream, and then all 5 try to do something to create that state, reconcile the declarative state, and then they all do the thing, and you get 5 updates when you only needed 1. So having multiple controllers isn't the answer. What if we just say, okay, multiple replicas in terms of, what if we just say, okay, there's 1 replica, and we let Cube reconcile that, okay, if it goes down, it comes back up. I guess I did this in the opposite order, but the problem with that is that it takes an awful long time to notice that the pods go down, at least in the default configurations. And while you can create changes that say, okay, well, pay attention faster for all the stuff, it seems to be a global timeout in terms of noticing that a pod's gone down, it needs to come back up. So leader election allows us to solve this. So how does that actually work? It's the actual backing thing, as I understand it, is provided by etcd, but it is exposed in a cube manner in that there is a client Go library extension, and it creates either an endpoint or a config map that has basically all the controllers that are trying to do this, try to basically take the lock and then try to keep the lock. And one goes down, there's a timeout period where the next guy to try to get the lock sort of will wait just long enough that we're pretty sure it's dead, and then they'll try to grab it. There's a formula in the code that you should go read that says how you should try to set these 3 different periods. And then once you do this, you basically specify a deployment where replicas is greater than 1. When this actually occurs, 1 replica will be the leader and the rest will be passive. And you need to make sure that you do enable pod anti-affinity, because it doesn't really do you much good to have multiple copies of something all on the same node if the one node that they're all running on goes down. So you want to make sure you lose 1 replica only, as few as possible. This brings us into the first demo.
All right, I'll try to show you.
Need to be bigger.
Is it big enough? Hopefully. So we have 2 parts demo. The first part of the demo will demonstrate how fault tolerance help you recover faster. So let us first start with a basic setup. Give me 1 second. Where Morgan. It's I can't. Okay. So we have a cluster that has 3 nodes. It's still small. Can you guys see this or? Okay.
Bigger.
Much bigger.
Okay, that's good.
Yeah, that's good. kubectl get nodes. We have 3-node cluster. This didn't cluster that's working. And we try to deploy a simple application on a simple controller on that and make it fault tolerant. So if we work in namespace demo, we create a namespace, and then we create RBAC rules to run within that namespace. I can show you RBAC if I have time in the end, or we also discuss about how to control the custom resource using RBAC rules. But in general, at this point, we are installing a custom controller. We created a custom controller called kubecon demo, and that will watch for changes to a custom resource object. When you look at the deployment, this particular resource is running 2 instances. One of the instances will be active, the other instance will be passive. And we also look at the pods that this is using. Control-V. Cut and paste is always difficult between windows. So there are 2 pods that are 2 instances of that custom controller running right now. And like Morgan said, they are using a lock mechanism to elect a leader. And we can see the, okay. Get endpoints on demo. Oh, you know what? I messed it up. Is it deployed to demo? It did deploy to demo. So, oh, it takes time. What happened? Okay, we sure can figure out this way, but the easy way to figure out for now is logs. I'm not typing there. Kube control logs. And we pick up the one of these pods. Minus demo. And this is definitely not the leader, so we got an RBAC failure. Okay. Where do we see now? I did create the RBAC. Kube control. That's the RBAC I got. It is created. I think we did. Okay. Okay, much better. So somehow my RBAC did not run. So we got an endpoint. Now we know that one of the 2 pods that we have is the leader. So it's listed out there. with a holder identity. So when you do kube control get pods on that demo, we got 2 pods. The first pod is the leader. So if I do kube control logs, minus n demo. Okay.
Create CRD.
Okay, let's create the CRD. We got a food definition. It's a CRD definition that we are creating. And we started the KubeCon demo controller that's starting the workers to process any changes to this resource at this point. Let's see, make a change by adding a resource instance. So I'm going to create a food type resource. I know. Oh, sorry. Create -f. We created a resource, get foo, and we got an example foo there. And at this point, if you see, let's see what example foo looks like. Describe. I better not do cut and paste. Describe foo. Example foo. That's much better. So this is the example foo, and essentially what we did here is we have a custom controller that is looking at this foo custom resource and created a deployment for us and running Nginx. What we do at this point is we see if we can generate some traffic on this by running a program to change the deployment. And also on another window, we'll watch how the pods are doing. Okay. So the traffic we are generating is basically changing the replicas on the pods. So there are 2 pods here. They are toggling. Back to the previous window, what we can now do is see there are passive and active controllers running. So we want to shut down the active controller node, creating a artificial node failure or hardware failure. So if we need to know where that particular pod is. If we run this, we see that F1 is our primary active controller that is running on kube node 1. The trick I do, since I'm running in Docker, I do Docker PS to see where this thing is, and then I can do Docker rm -f. Kube node 1, is that kube node 1, right? So as you can see now, the actual deployment has stalled for a minute. We create we want to generate the traffic. Where am I? They should start anytime. Practically, yeah, it started. It's a much quicker turnaround if the leader election, the other passive controller has taken over as a leader and started working again. That's the part of the first demo.
Okay. 3, 2, 1. Testing. Okay. So we saw that. We saw that it came back up eventually. We had a little difficulty with some of it, but we're here. So I'm going to describe the two different sort of patterns that Wei has seen in his implementations of multiples of these things behind the scenes. So what he likes to call it is controller versus controllee, and the controller pattern is where we say the CR is the thing that you interact with directly. You create custom resources, you poke them, you interact with them. They are the essence of whatever your program is designed to do. So you will use kube control to create them, or you use client Go, and then you'll have your own custom controller that watches whatever the CR is and performs some action. So if you go to the actual example controller, is this type of pattern. This concept is, I would say, more evident in things like the operators. So etcd operator, you create a custom thing, you install the controller, and it looks at the created CR object and does a bunch of stuff to create some kind of etcd instance or a Prometheus instance. So the other pattern that we've seen is the controllee pattern, where you create normal objects in Cube. You have a first controller that sees changes to those objects and creates a custom resource object that you don't normally interact with. It is sort of hidden behind the scenes. And then there's a second controller that will operate off of that custom resource that gets created and does something that the user shouldn't normally care about, and does it behind the scenes. And it's sort of this double jump of management where you don't want to be tied to the original object, but you do need to sort of keep the state of what is getting changed somewhere, and you can't keep it in the original object. So the use case that we have for this was custom load balancer types in the internal cloud that they have. So you create a service, and the service is some kind of special load balancer. And so there's a CR that represents the fact that this load balancer gets created, and then that CR is what is used as sort of the endpoint for management of the actual load balancing technology behind the scenes. Okay, describe that. So some sort of best practices or useful ways to look at namespacing versus cluster availability is, if your object is the controller, you probably want to have it in a namespace such that people can have one in their namespace, and then people not in that namespace can't touch it. But if it's a controllee pattern, you want to put your CR in the sort of the global namespace or in a special namespace that nobody can normally touch, except for your controller, so that it's isolated and people can't touch it because they shouldn't be. It's really a computer consumer only, and you can use RBAC to enforce all of these things. Okay.
All right, we'll try the second demo. Hopefully this is faster. So what we did in the first demo is we created a custom resource that is doing the work. In the second demo, like Morgan said, we have a controlling pattern that we want to demonstrate. All right. So in this case, we are going to start a controller first. I'm out. OK. I'm in that terminal. The controllee is another custom controller we wrote. And then we also create a new service called Bauer service, which is going to look at the foobar object that is being changed here. So we didn't create the Bauer. OK. I'm not. So we created a bar object, and we have both the controllers running right now. So if you look at control get bar, there are no bar instances yet in the namespace demo. I keep forgetting that. So there are no bar objects running right now out here. So let's see how we can create a bar object. We are not going to create the bar object directly. So we need to change something in the cluster that would trigger. In this case, we do a deployment, and the deployment triggers the controller to create the bar object, the custom resource. And we do not control the bar object by ourselves. And in turn, the bar object will create a service object for the deployment we are creating. So if you look at the kubectl get service on demo, in fact, it did for some of the services that are running in that. This essentially what happened. But we will show you with a nice example here. Let me go to examples directory. We got a guestbook app here, which is deploying a guestbook, and it is listening on container port 3. So let's create this deployment, which is control create -f. So we created a guestbook application, and if you look at the deployment, there is a guestbook running. Okay. I didn't. Okay. I then messed it up. Delete deploy. I need to create in the namespace so that it can work. -n demo. Now, if you look at, we got the guestbook running in that. So if you look at the bar object, the controller actually would have created a bar object for us. And the bar service object is created, which in turn has created us a service. And there you go. The guestbook service is listening on port 3000 in the namespace, so which is basically demonstrating the controlling pattern.
Excellent. I already hit the slide. Okay. Last bit here. Make sure when you're writing your client code, they've noticed a lot of things being hard-coded, so you want to be relying on things like interfaces over direct struct references. Right now, at least in our particular example here, there's no particular validation being done on CRDs. I've heard that's a big thing that's coming in 1.11. So right now, both of our CR objects are wildly different once you actually look at the code, but when we actually define them, they're the same actual definition with something that has no bearing on the actual type definition in types.go. So you have to make sure that you do validation in your client code as it is right now versus it being done automatically as per standard Kube API server. And the next that leads into sort of these migration considerations where when you change something, you have to make sure that your code can handle the differences between CR versions essentially that you do changes. And then the last part is it doesn't do you any good to be for all your controllers that have different replicas to be doing watches if they're not the leader. So you want to make sure that you only start doing your watches after you actually get the leader election lock. This harkens back to that earlier statement I made where you don't want to have multiple controllers acting on the same resource. And then the last bit not on here is that you need to be very vigilant in your code for validating that the object that you are getting over the watch stream A still exists and B is not a duplicate of some other event. So there was a bug at some point in the code where you could get multiple updates for one change, and you need to be aware of that is a possibility of happening. It's not a once and only once kind of system. That's about it. And we have links and emails, and if you have any questions.
Yeah, thanks. Are there any best practices around maybe setting status back on your CRs and using those?
Yeah, I mean that's a general Kube pattern in terms of it's basically establishing the state machine, and you should create. You should, in my opinion, you should diagram out the state transitions that you have, and make sure that you enforce that the state transitions happen. And that in terms of spec to status, that you almost sort of write what you're about to do, that becomes your status. You go do the thing, write that it's been done, and I know that the condition model sort of is sort of different than that, and over the last couple of years I've seen the different people in architecture and API go back and forth on the difference with that. But I would reach back out to them for more guidance on that kind of thing. But yes, you should do the standard spec and state model with the CRs. We didn't show that, but that is what's going on behind the scenes there. Oh, you didn't show cleanup, Srini.
I didn't show cleanup.
That's okay. Well, you actually, if you delete, we showed the automatic creation of the server.
Owner reference. So if you delete the deployment, the service object should go away with it. So, in the interest of time, I had to rush with that. So.
Questions? All right. Thank you. Oh, okay, over there.
How faster is that approach with the config map versus the one replica and wait for a new pod to spin up?
The standard timeouts on Kube are something like 5 minutes, which in the best case, it is a couple seconds over 5 minutes if all the different timeouts happen like one after the other. If they happen in sort of a bad state, it's like 5 minutes plus 5 more minutes plus 5 more minutes a couple of different times. So I've seen,
seen 10 to 15
when doing preference, when doing, preparing for this, I've seen, 15 or 20 minutes for the cube stuff to realize that, yeah, a node's gone. I don't normally run that kind of stuff, so maybe there's a way that I'm not aware of that will pick it back up faster.
Yeah, I just wanted to mention that it's possible to do server-side validation of CRDs with mutating admission webhooks.
Yep. But it's, yeah, true. Not provided by default, though. It's not built into the API server stuff like the standard API server has validation built in. Anybody? One more? It's the end of the day. This is true.
Thank you.